Okay, now we're going to talk about capacitors. Capacitors are the opposite of resistors. Capacitors store electric charge. And if you're storing electric charge and you have a difference in electric charge, you're going to have a voltage. So capacitors create a potential difference. They create two separate voltages, a positive and a negative voltage. And if you have a difference in potential energy, you have voltage. They do it by storing electric charge. We'll look at that in just a second. The key thing is we've spent a lot of time talking about resistors. If you just realize that resistors and capacitors are exact opposites, it will make it a lot easier. So capacitors store voltage, resistors use voltage. Okay, now the way a capacitor is going to store electric charge is by being connected to a voltage source. If it's connected to a voltage source, what's going to happen is the positive side is going to create this side positive. These are parallel conducting metal plates. So that's connected to the positive side. It's going to create a positive charge on one side. Well, if there's a positive charge on one side, there's going to be a negative charge on the other side. And those are going to be equal. In other words, essentially, we're pulling electrons out of the battery until the charges equalize. Now, in the real world, one of the most common things we do with capacitors is we will put them in a circuit opposite of a resistor. So over here, we'll put some type of light bulb. Any type of load would work. Let's say we have a light bulb there. Well, what's going to happen when you turn on the battery is electrons are going to do two things. They're going to come running out of here and build up a charge of negatives there. Well, if I have negatives there, it's going to repel negatives away from here, so this is going to be positive. I'm also going to get conventional current flowing through the light bulb, and the light bulb is going to turn on. Now, one of the biggest uses of capacitors is a backup power supply. Because now, let's say, for example, that now this battery gets wiped out for some reason. Now what's going to happen is electrons are going to come racing down through this, and the light bulb is still going to work, at least for a short period of time. So we generally use capacitors for two things. We use them to store electric charge, so we can use it as a backup power supply, or we use it for a big discharge all at one time. Flash cameras and tasers are probably the two most common places we see that. Now, just like a resistor, capacitors store charge based on their geometry. The most common type and the easiest way to understand it is to have two parallel conducting metal plates separated, putting a dielectric material in the middle of them, and then having a certain distance apart. Now, let's realize that this would be then connected to a power supply. So those two wires would be connected to a power supply. Long one's positive, short one's negative, high potential energy right here. That's going to be your area of high potential energy. Since that's positive, the top plate of this is going to become positive. The bottom plate will become negative. Those charges are going to be equal to each other. So essentially, I'm going to charge up the capacitor and store that charge on there. Well, some of the things make sense. It's going to be directly related to the area. For capacitance, we have something called C, which stands for capacitance. It's directly proportional to the area. The bigger the area is, the more charge you could put on there. That just makes sense. You could pack more electrons in there. The other one you have to, I don't know, at least think about a little bit. If I decrease this distance between them and bring them closer together, I'm essentially going to pull more electrons out. So if D goes down, C goes up. So C is proportional to 1 over D. Now let's look at an equation that puts those together. Here's the equation in a nutshell. Capacitance is measured in farads. it's equal to the permittivity of the dielectric. That's going to be different for every potential type of material you could put in between them. So the material you put between them does make a difference in how strong the capacitor is. Directly related to the area, like we talked about, the bigger the capacitor is, the more charge you could put on it. That makes sense. And D, the distance between the plates in meters. And again, as the distance gets closer together, you can put more charge on it, so capacitance goes up. Now, although capacitance is based on the geometry of the setup, the same way that the geometry of a wire determines the resistance of a wire, capacitance is also a ratio of Q divided by V. Q is in coulombs, V is in volts, so it's coulombs per volts, which we call a farad. Now, if you also remember that a volt is actually a joule per coulomb, when you reduce it down, reduces down to coulombs squared over joules. That's kind of messy looking, so we call that a farad. Now, a 1 farad capacitor is big. Usually, our capacitances are going to be in the microfarad range, the 10 to the -6th range. That's a more realistic everyday number for 1. Key thing to remember, C is equal to Q over V. Q is equal to C times V. C depends only upon the geometry. So C depends only upon the geometry and the type of material you put between them, just like a resistor. So what happens when Q goes up, when V goes up? So if I attach it to a stronger battery, I'm going to get more charge. Now, when they discharge, it discharges very fast, like that. So I get a large amount of charge. If I look at Q versus time, I get a discharge that occurs relatively quick. This big discharge of current is what's going to give me my taser strength or my flash. Hope this helped. Now we're going to put them together in series and parallel and take a look at what happens. Okay, let's reinforce one more time that they're opposites of a resistor. And we think about it, that this amount of capacitance is proportional to A over D. I can put more charge if I have a bigger area. I can draw more charge out of the battery if the plates are closer together. Let's go back to our resistance equation for the resistance of a wire. The resistance of a wire is proportional to the length of the wire divided by the area. Opposites. So you don't really have to remember 2 cases if you can remember 1 case. And we spend more time, and there's more on the test about resistors. So therefore, just file away in the back of your brain that capacitors and resistors are opposites. Hope this helped.